Hi, my name is Daniel, and for this project, my colleague Meng and I were exploring the idea of blind grasping using a low inertia arm. The main motivation being that expressive information can quickly become unreliable due to occlusion, particularly in cluttered environments and poor lighting conditions. Additionally, force torque sensors usually only work well in the quasi-static regime. So the main idea was, what if we can use purposive information from a low inertia arm to find objects when these other sensor modalities are unreliable? On the system side, we created a robot model of the low inertia arm that we plan on using on our custom simulator, which models the dynamics for our system and visualizes the robot. Then we build a simple Cartesian space trajectory follower. However, since the integration with hardware still requires a lot of engineering efforts, we instead output the joint trajectories directly into the hardware, then add gravity compensation and track them online. Then we do some simple contact detection using the purposive information. We use a 6 degree of freedom robotic arm with a simple 1 degree of freedom gripper, which all uses low gear ratio actuators. And the arm in general is very light and most of the mass is concentrated at the base, making it very suitable for high impact and contact work situations. We built a simple trajectory tracker using the pseudo-inverse velocity controller that we learned in class, where we receive a list of waypoints, and we calculate the velocity in the world frame to reach the next waypoint, and then we do some low-level joint velocity control. Then we built a simple finite state machine in which we go to an arbitrary set of waypoints. We probe the environment with our gripper, and if contact is detected, which we only check in the hardware, then we execute a pre-computed local trajectory to try and grab that object.
So now moving on to the hardware. On the left, you can see there's no gravity compensation. So the mass of the arm overcomes the friction of the actuator and falls to the ground when I let go. On the right, you see where gravity compensation is implemented. The motors are exerting a torque to make it seem like the arms are massless. This is helpful for demonstration purposes and for better trajectory following and position control. Now we are going to incorporate everything to run the trajectory outputted from the pseudo-inverse simulation. So on the right, we can see the robot, instead of snapping to the initial pose like it did in simulation, it takes a more conservative and safe trajectory. Then only after, when it gets to that initial pose, it begins to start following the horizontal velocity across the workspace, like you see in the simulation. For contact detection, the benefit of using low inertia actuator is the access to clean and sensitive current feedback from the environment. On the left, the gripper hits the 200-gram weight without stopping and knocks it over. On the right, by monitoring spikes in the current, we're able to detect and stop before knocking the same 200-gram weight over. Now it does the same for the 100-gram weight. However, it reaches its limit when it can only detect, but ends up knocking over the 20-gram weight. Another feature that will be useful in the future is playback of human-guided trajectories. On the right, we can see the robot does a great trajectory following of the human demonstration on the left. This could be very useful for authoring complex behaviors and learning from demonstrations. So we weren't able to fully integrate the contact detection into our pipeline because of many hardware bugs and having to build the pipelines from scratch. However, after that, we do plan on exploring ideas like rapid pick and place, contact detection and clutter, and human robot safety. That's all for the presentation. Thank you, Russ, and all the TAs for amazing class and amazing semester.